We have discovered microfossils that are composed of hematite. Basically, it's iron oxide, it's like rust.
Through laser imaging of the samples, we were able to identify the microfossils as the oldest known microfossils on Earth.
This is a slab that's been polished. There are these structures here. It is cut on the right-hand side, but you can see kind of a structure that bends the layering in this rock. And it is within these features, in part, that we find the microfossils.
In diameter, the microfossils are half the width of a human hair. They can be anything up to 0.5 millimeter in length.
The microfossils we discovered are about 300 million years older than the previously thought oldest microfossils. These rocks have a minimum age of 3.77 billion years, but some scientists in the field consider them to be as old as 4.28 billion years. So they are within a few hundred million years from within the accretion of the solar system and of planet Earth and the sun and the moon and so on. These rocks are being mostly composed of silica and hematite, this iron rust. We find these kinds of environments today in the vicinity of hydrothermal vents, either in the deep ocean and in some places not in so deep localities that exhale a lot of iron particulates in water, and this is thought to be the material that these bacteria actually eat and breathe. The rocks are located in the province of Quebec on the shoreline near to the Nastapoca Islands. When I saw these structures in the field, I said, I have to sample this.
One of the big questions when it comes to early life studies is whether or not the organic carbon we find in these rocks is actually biological in origin, especially in hydrothermal vent environments where you can have special reactions called the Fischer-Tropsch reaction.
So we used a very robust, rigorous approach to test whether these microfossils we discovered were non-biological structures.
And we were able to do this with our laser imaging system by looking at the minerals the organic material was associated with. And we find it with these key minerals, apatite and carbonate.
If we are right with our new model for the origin of these spheroidal structures in these rocks that contain these fossils, then we might want to look for these kinds of things on other ancient planetary surfaces, such as the surface of Mars, for instance.
I'm keen to look at more examples of hydrothermal vent deposits, and if we can take our knowledge of how organic matter and microfossils are preserved on Earth and apply them to hydrothermal systems on other planets like Mars or Europa.
In 2007, there was one of the Martian exploration rover found beds of hematite concretions. They were called blueberries at the time, and it made a big news splash as well. The origin of these structures is not fully understood, even on Earth where we find them. But we don't know really how organic matter can potentially be involved in making these structures.
The most exciting thing about this discovery is that we know that life managed to get a grip and start on Earth at such an early time in Earth's evolution, which gives us exciting questions as to whether we are alone in the solar system or in the universe. If life happened so quickly on Earth, then could we expect it to be a simple process and start on other planets, or was Earth really just a special case?